let's look at this one. We're going to have a gas that's undergoing a process in a piston cylinder assembly. And during that process, the pressure-volume relationship is going to be PV to the power of 1.2 equals a constant. The mass of the gas is going to be constant at 0.4 pounds. And we know our initial pressure is 160, initial volume is 1, and second pressure at the final state will be 390. We are also given the heat transfer term. So notice it says it's from the gas. That's going to be 2.1 BTU. We're going to neglect these two terms. And then we want to find the change in specific internal energy. Let's go ahead and write down what we have. We've got our initial pressure. That's the 160. Got our initial volume. And then we've got our final pressure. We do not have the final volume though. All right, so we don't have that. Now we're also given Q, because that's our heat transfer term. Notice it says it's from the gas. So we're taking energy from heat from the gas and sending it to the surroundings. That's going to be a negative 2.1 BTU. All right, and what we're looking for, we want delta little u. Okay, so we need to find that. Now, our equation that has Q and delta U in it is going to be the energy balance equation. Remember, this is capital U. That's regular internal energy. We want specific internal energy. We'll change it up in a minute to get that. And all of the energy terms are equal to Q minus W. These two go away because we're ignoring them. Now we have this. We want that. So that means we need to find work before we can get what we need. Now our equation for work is going to be that standard integral equation we've been looking at. So the integral of pressure times the change in volume. Now if you go through and look at this, we're going to integrate from volume 1 to volume 2. I'll plug the values in a second. And then we need our equation for P. That equation for P is going to come from this relationship up here. All right, so we know P times the volume to the power of 1.2 equals some constant. Let's just solve for P. So we'll have C over V to the power of 1.2. All right. Now, remember the C is a constant, so you could pull that out. So let's put C here at the front. And then instead of writing it in fraction form, I always like to write it as negative 1.2. It's easier for me to do the integral that way. Now if you integrate this, let's come down here, you're going to end up getting the constant times the volume. Now your power is going to be negative 1.2 plus 1, and you're going to divide that by negative 1.2 plus 1. Then you have to evaluate. Once you plug in those limits, you're going to have C times V2 to the power of negative 0.2 minus V1 to the power of negative 0.2, and then put that over negative 0.2. Now we know V1, but we do not know V2. So let's find V2, and then later on we'll also find our C value. Let's get V2 first though. We're going to get V2 using this relationship here. This relationship will allow us to relate state 1 to state 2. So let's do that next. So we can write P1 V1 to the power of 1.2 equals P2 V2 to the power of 1.2. Now we want to solve for V2. So if you do that, you're going to have V to the power of 1.2 equals P1 over P2 times V1 to the power of 1.2. Now we got to get rid of this. So once you get rid of that, you're going to end up with, this is V2. V2 equals V1 times P1 over P2. And then the exponent here is 1 over 1.2. Alright, so now you end up with that. Now we can plug these values in. We know all of these, so we can plug them in. And you're going to get 1 cubic foot. And then for pressure, we got 160, and then we have 390. Those units cancel, so I'm going to leave them out because I'm running out of room here. There's your power, and then once you do the math, you get 0.476 cubic feet. So that's our volume. So we're decreasing volume, which would make sense since our pressure did increase. Now that gives us this term for here. Now we just need to find C. So let's do that next. For C, we're going to use this same expression here. And I'm just going to use the state 1 values. So P1, V1 to the power of 1.2 equals C. So plug everything in, and we'll have 160 times the 1, that's cubic feet, and then we got our power of 1.2. Now this value is going to be 160, and your units here get a little weird, but they all end up working out in the end when you plug them back in. So I'm just going to leave that 160 there. Now let's take this 160, we're going to plug it back in up here along with V2. Let's call this equation 1 since we're far away here. Alright, so from equation 1 then, we can write that the work is 160 times V2, which is right here. So 0.476, that's cubic feet. And remember, this is to the power of negative 0.2. And then we're going to subtract V1, which was 1 cubic feet. And then that's to the power of negative 0.2. And then we're going to divide by negative 0.2. Alright, so your weird units here on C, which I didn't even write out, they go away because we have weird units here when we're doing this power to the negative 0.2. Alright, so the units are all going to end up working out there in the end. Alright, so now what you're left with when you do all of this is you've basically got units of pressure from over here, because see we had these pressure units here, and then you've got this cubic feet thing to the 1.2. Now since we've got inches in this right here, we need to do a conversion. So let's do 144 inches squared. Let's put that over square feet. And then we want this in BTU. So let's convert over to that. So we're going to have 1 BTU per 778 foot-pound force, like that. And that gives us a work value of negative 23.69. And that's BTU. So this is negative, so that means there's work done on the system. So there's energy due to work being sent in from external sources. All right, so we got that. Now what we're looking for though is delta U. So now we're going to go back to our energy balance equation, which is right here, and then we will plug everything in. Remember that your energy balance has regular internal energy. We are looking for specific internal energy. So let's write that relationship down. Delta capital U equals the mass times delta little u. We want this right here. Now that means if you plug this into your energy balance equation, that delta of the specific internal energy is going to be Q minus W over M. Alright, so we're going to have negative 2.1 BTU minus negative 23.69 BTU over the mass, which is 0.4. That gives us 54 BTU. So that's our change in specific internal energy.